Hello, this is Sean Mullery from Electronic Engineering at IT Sligo, and in this lesson I'm going to look at the timers. Specifically, I'm going to look at timer 0. So I asked you in some of the exercises to take a look at the setup of the timers in the document. So we're just going to take a quick look at that before we move on, which is here. So I'll just type in timer. And what I'll do is I'll go back to the beginning. So I'll just close that and go back to the beginning because this is normally how you'd be approaching it. So I'll start there again and open up the Finder here and type timer. Now the first thing we come across here is we come across a lot about the timer oscillators that are used for the externally for the system. We also come across a thing called a watchdog timer, which is a mechanism to determine whether the microprocessor is still functioning properly or not. In other words, if the program has run into trouble, the watchdog timer can spot that and reset the device. That's not what we want to look at for this though. We want to look at the hardware timers. So we're going to keep going until we see something about those. And actually, if we just go back there, we did see something. We can see that the PIC 16F88 here, go along that line, it has timers 8-bit and 16-bit, so it has two 8-bit timers and one 16-bit timer. Okay, so that was one of the questions that I asked you, what sort of timers that it had. Now we also wanted to know what their names were, and if we go one step further, we can see that we've got a timer 0 module, a timer 1 module, and a timer 2 module. So clearly that's the name of the timers that we're going to be using. So I'm just going to go straight through to the timer, sorry, it's the timer 0 module is what I wanted to go through to. So I'll just go back there again. I clicked the wrong thing. So the timer 0 module. Now, one of the things I asked was about whether it could be used for anything else other than a timer, and as you can see here, it can be used as a counter, but we're not going to use it as a counter in the first instance. We're only going to use it as a timer, but it's worthwhile just knowing that you can use it as a counter as well. So timer 0, it's an 8-bit timer, this one, and we can read and write to it. It's got a programmable pre-scaler. Now what that basically does is it determines how often the timer is going to update its value. Okay, it's got an internal and external clock select. We're going to be using it as the internal, and it interrupts on overflow from FF to 00, and that was one of the questions I asked you. Can it cause an interrupt? And indeed it can. Now, some additional information on the timer 0 module is available in this. We've got a reference manual there, so we're not going to go looking at that for the moment. What we want to look at here is the timer 0 operation. So timer 0 operation is controlled through the option register. Timer mode is selected by clearing bit T0CS, okay, of the in the timer mode. Okay, so T0CS, that's clearly something that you're going to have to write down, because that's something that we're going to have to use in order to deal with the situation. So T0CS, it needs to be cleared, put to 0. Okay. If so we can see here that in timer mode, the timer 0 module will increment every instruction cycle. If the TMR0 register is, sorry, that's without the prescaler. So the prescaler can vary that so that it does it less often. If the TMR0 register is written, the increment is inhibited for the following 2 instruction cycles. Now, that's something we don't really need to worry about for the moment, but it is worthwhile just to keep in mind if you're looking for very accurate timing. When you've written it, it takes another 2 instruction cycles before that actually takes place. So you may need to include that and actually add an extra 2 instruction cycles to it, or take 2 away depending on what you want to do. So the user can work around this by writing an adjusted value to the TMR0 register. So that's what they're talking about there. So if it takes 2 instructions longer, then what you can do is you can set it to 2 shorter in order to get it to run the exact right amount. We won't worry too much about that level of accuracy for the moment. Now, counter mode is selected by setting bit T0CS, as we've seen earlier. So we don't want to set it up as a counter, so we won't be doing that. And so we'll ignore the rest of that section. That's all to do with setting it up as a counter. What we then want to look at is the TMR0 interrupt, which is generated when the TMR0 register overflows. this overflow sets bit TMR0IF. So remember that one, TMR0IF. That's the flag that we're going to have to check for in our interrupt when it occurs. And the interrupt can be masked by clearing bit TMR0IE. And what that basically means is that we can also enable it by setting bit TMR0IE. So bit TMR0IF must be cleared in software. That was one of the other questions I asked you. Do we have to clear that once it's been set and we bring it into the interrupt? And we do by the TMR0 module interrupt service routine before re-enabling this interrupt. The TMR0 interrupt cannot awaken the processor from sleep mode. We don't need to worry about that for the moment because we won't be putting it into sleep mode. So I'm going to use those details in order to set up the timer to just run and every time it overflows to call the interrupt and to do something at that point. So that's what I'm going to be doing in this program. So I've got my usual, I've set up TRISB as all outputs, not using the external interrupt on this occasion. And so some of the things that I want to do, I want to say T0CS, you remember that from it, we want to clear that value, so put it to there, okay. And that's because we want to make it put it in as a timer and not as a counter. What else do we want to do? We want to look at the enabling the interrupt, okay. So TMR0IE is the enable for this, and we set that value. Now, because it's an interrupt, we need to enable all interrupts, and that means the global enable interrupt has to be set. So GIE is set as well. Okay. So we'll see if that's enough for us for the moment to set it up ready to go, and we'll go to the interrupts here. And in the interrupt, hopefully the ISR will get called whenever that overflows. But in the ISR, we should be checking to see if that flag has been set. And if you remember, it's called TMR0IF for interrupt flag. We're checking, was it set to 1? If it was, it means that's the flag that caused the interrupt. We need to clear it. TMR0IF is assigned 1. And what I'm going to do is I'm going to update a count. Okay, and if you remember this from previously, what I did was that count is a variable that's shared between the interrupt file and the main file. So I've said extern unsigned character count, so that's a variable that's out in the main file and is declared there. So every time the interrupt occurs, that count should increment. And what I want to do then is I want to, and you will just check that I have count up here. I do, unsigned character count is assigned 0. And what I want to do is port B. So I want to put the value out to port B, and I'm going to put out count. No need to do anything more with the count variable here because I'm not using that bottom bit for anything else, so it's perfectly valid to use as it is. Okay. Could it be that easy? Well, let's give it a go and see, have we forgotten anything? Okay. And that is running now. But what we notice is if we look at RB0 to RB7 on our output here, we are not seeing any outputs. It's not actually varying, which means the count variable is not varying, which means that there is nothing happening. That interrupt is not actually occurring, which means that we've forgotten something. So let's just check this for definite and make sure that we're not going into that interrupt by just setting a little breakpoint here in the interrupt, and we'll just do a redebug there and let it run. And it has hit the interrupt here, so what that tells us is that the interrupt did occur. So what's occurring at that point? So if it's occurred, and we'll just move slowly through it just to see what's wrong. So we've moved to there. We've updated the count. We've gone out to the end of the interrupt, and we've gone back in here, and we're into the interrupt again. And we're straight back to the interrupt again. Okay. Now you'll notice here at no point are we actually ever getting back as far as our main file. So we need to try and figure out why exactly it is that we're getting into the interrupt, but we're not getting back to the main file. And the reason is, I've made a bit of a mess here. Okay, what's occurred is that the flag has been, we've checked to see was the flag set in order to make sure that the interrupt had occurred. But what we were supposed to do, and indeed one of the things I asked you to check was, do we have to clear the flag in software? What have I done? I've only gone and set it again. In fact, all I've done is I've set it, but it was already set. So what will occur then at that point is that because I've done that, as soon as we leave the interrupt, it will think that the interrupt has occurred again, and it'll just bring me straight back to the interrupt. So let's modify that and put it back to 0. Okay, so now every time the interrupt occurs, we check to see was this the flag that caused it. If it was, then we clear the flag and then we update the counter. So what was happening previously was the counter was certainly getting updated, but we were not clearing the flag. That never gave us a chance to actually go back to our main program and actually output anything to the port. So we're going to have to do a recompile of that. Okay, and again we've hit that breakpoint. So what I'm going to do is I'm going to remove that breakpoint now and let it run freely. And what we see is that if we look over at the pins here, we can see that they're flickering. Whether they're working correctly or not is quite difficult for us to tell. And the reason it's difficult for us to tell is because it's going far too fast for us to actually be able to determine whether it's actually counting up properly or not. So a way to kind of just see if it's working correctly is to, in our interrupt service routine, just put a breakpoint here on the count plus plus. What that'll mean is that every time we update the counter, we should be able to look at our output. Now the output doesn't change until the next time, but at least if we just keep stopping at that counter each time, that should show us. Okay. So the very first time we've stopped at the count, but we haven't updated, we still got 0 out on it there. We'll run again, and you can see that 1 has now come out on it. We'll run again, and we can see that we now have 1 0. Run again, and we now have 1 1, and should be that if I run one more time, I should see it go to 1 0 0. And that is indeed what's happening. So we can see that this is indeed counting up correctly, but it's happening so fast, and that's because this timer is really only running for 256 instruction cycles before it overflows and then updates the counter. 256 instruction cycles will happen very, very fast if we've got a fast processor. So what we'll need to figure out next is, of course, it's very difficult to know what speed this simulator is running at, but what we need to look at then is how often do we want the counter to actually update, and therefore is the timings that we've given it appropriate. What I'm going to do in the next lesson is I'm going to look at the 16-bit timer. That will take a little bit longer because it can go to 2 to the power of 16 or 65,536 instruction cycles before it overflows. And when we see that, we'll see that the count goes up a little bit more slowly, and then we'll start looking at how we want to do very specific numbers of milliseconds or microseconds or whatever in order to get something particular done. So in the next video we'll be looking at the 16-bit timer.